Okay, I think it's just 12 p.m. exactly, and let's start this week's statistics seminar. And today we have Professor Mladen Kolar from the University of Chicago, the Booth School of Business. And his research is focused on high-dimensional statistical methods, graphical models, varying coefficient models, and data mining. So today, Dr. Kolar will tell us something about personalized federated learning. So please welcome our speaker, and please go ahead, Dr. Kolar.
Okay, thank you very much, Tiandong. So I guess like today's talk is brought to you partially by Irina. So she specifically requested not to talk about graphical models. So here we are, and we'll talk about personalized federated learning. This is something actually I'm quite excited about. And despite the fact that the talk will not focus much on statistics, I do encourage you to think about how statistics could be brought to this problem. I think there are many interesting statistical challenges that could be developed in this framework, and the people who are working in this area are largely not thinking about this direction. So the talk today is going to be about personalized federated learning, and specifically I'm going to focus on optimization techniques for this problem. And then at the last part of the talk, I'll tell you about some statistical challenges that I think, statistical problems that could be addressed in this framework. Now, this talk would not be able to happen without my two collaborators. So Philip Hansley is a new addition to Toyota Technology Institute. He just graduated and joined as a research visiting faculty, and Boshin Zhao is a hardworking first-year PhD student in my group. And the talk is going to be based on the paper that we recently posted on arXiv, and here is the link if you are interested in this in more details. Now, what I want to start off is I want to introduce a framework of federated learning. Now, this is a shall we say, a problem that has caught a lot of attention in the machine learning literature, but you will quickly see that as statisticians, we can contribute to solving some of these problems as well. So the idea of federated learning is the following. What we want to do is we want to train a model in some heterogeneous massive network. Two examples that people commonly think of when thinking of federated learning is a setting where you have a lot of remote devices. We will call them sometimes edge devices. And these edge devices are running some kind of machine learning models on them. For example, what each one of your iPhones or Android phone, what they might be running is a prediction for the next word. When you are writing, say, an email in Gmail, you will have a suggestion of what the next word should be written. And similarly, on your iPhone, you have, once you start typing in a text, you will have a prompt to suggest to you what the next word should be typed in. So now, how do you train a model based on the data that is extremely spread out throughout the world? So specifically, what Google would maybe want to do, or what Apple would like to do, is they would like to train a single model based on the data that's sitting on each one of the users' devices. Now, due to privacy concerns and due to communication costs and so forth, it's impractical to send all of this data to a global server, to something that Google has access to, then use some data center that Google has access to train, say, a logistic regression model or a deep learning model or something like that. Rather, what we want to do is we would like to train model on each one of the devices. Now, the problem with this is also that devices themselves potentially not strong in computational power. There's a lot of communication overhead between going back and forth the global model and the data that sits on different devices. So this is a challenge. And as a result, people have thought a lot in the last 3 or 4 years about this problem. And I'm going to scratch the surface and talk a little bit about one specific aspect. Another example of a problem that arises in federated learning is if you have different institutions, maybe healthcare institutions or private entities that don't really want to share their local data due to privacy concerns. Yet, for the benefit of the society, we would like to learn a personalized model that is going to be used to treat different patients. So again, in this setting, what we need to do is we need to figure out how should we train a personalized healthcare model based on the data that's sitting at different participants without sharing that local data. And so one solution to that approach would be based on federated learning. There are many other examples. So, for instance, voice recognition on mobile phones, potentially adapting to pedestrian behavior in autonomous vehicles, personalized healthcare on wearable devices. You can think of predictive maintenance for industry of Internet of Things type of machinery. So many things where you need to develop a model that is going to be useful at the remote device, and it's going to be costly to collect all data to centralized location. Yet you would like to build a model that's going to be useful for these problems. So some major challenges that are present in dealing with these problems are the following. So one thing that I'm primarily going to focus on is the fact that the data that are collected are not ID. Specifically, the way data generated by different users is quite different. So for example, my patterns of writing English are probably different from the patterns of English that a native speaker might have. For instance, maybe the usage of my language is different from somebody who is in a different area of study, such as maybe social science or non-engineering field. Another problem is that data is quite unbalanced. Some users will have a lot of data, some users will have little data, and this is more of an engineering challenge, but there might be some statistical challenges. This is something we will not talk about much at all in this talk. And then there are some other problems in that there is a large number of mobile device owners, and typically there's much larger number of users than how much samples we can collect on each one of the devices. So this data is massively distributed. It's different from, for example, distributed computing that one might be running in a data center where we have access to a computer that has, I don't know, 30 or so cores. Here we have millions of devices that can perform some computing. And another kind of thing that we will care about in today's talk is limited communication. So specifically, because of the instability of mobile network connections, we cannot always rely on the fact that a particular user is going to be present when we need to update the model. And also, because of this instability of network connection, it's going to be impractical to communicate a lot in order to learn our model. So that said, what the classical federated learning task is formulated in the following sense. So what we want is we would like to find parameters of some statistical model. Let's say that this model is parameterized by a vector W that lies in a d-dimensional space. And we have M devices that are sitting somewhere. And what we would like to do is we would like to find a parameter W that optimizes the following objective. Okay, so this number M that we have is quite large. And the problem is that the type of solution to this problem is going to be that we will have typically a central server that facilitates optimization. So the central server will have some kind of current model, and it's going to be communicating with different clients, and the client will own their data. So the data will never go to the central server. So these the FI primes, these let's say likelihood functions that sit on each one of the user, and they're based on the data that might lie on that client. So Google does not have, for example, access to this data, and it doesn't have control in how these FIs look like. So the Google has saying that this FI is going to be, say, likelihood of logistic regression model, but it does not have a say in what type of data will be located on each one of the clients. The main bottleneck in finding this vector W that minimizes this objective would be communication. So the amount of information that needs to pass between individual clients and the central server. So the typical approach to solving this problem, where we are trying to find a model to deploy to each one of the clients, is as follows. So we have a setting where there's a global model. In round number I, the central server, Google say, has a model, the coefficients of a deep neural network or coefficients of some large logistic regression model. And what it does, it sends that model to different clients. Typically, due to the fact that clients come in and out of the network, the model is sent only to a subset of the users. And in that round, what each one of these local machines, what they do is they perform some number of gradient step updates to the model. So the model that gets to each one of the machine is the same, and then they use whatever data that they have available on their machines to update the model, typically using stochastic gradient descent or mini batch gradient descent or some form of local updating. And once they've updated the parameters of the model, some form of updated model is being sent to the central server back. This could be the change in the weight vectors. It could be the parameters themselves or gradients evaluated on the subset of the data. And what the central server does is aggregates these models. In the initial work that was done in 2017, the aggregation was simply averaging of the updated parameters. So if you think of that local machine contains a vector W, which parameterizes some model, the central server is going to simply come up with a new model by averaging the updated models from different devices. And now we are in round I+1, and the central server sends the model back to the edge devices for further computation. And so this is a kind of the basic idea of what is happening in federated learning. We want to come up with a global model. We want to have one model that is going to be useful for everybody. And the way we compute this is that each one of the machines updates model based on the data that they have using some local updating scheme, such as stochastic gradient descent. And periodically, the models are returned to the central server, which averages the parameters, and that's the updated model for the next stage. So any questions that you folks have at this point, or things that I should clarify? Okay, so if there are no questions, then what I want to focus on is a specific issue with the classical federated learning approach. And the main issue is that this problem that you're trying to solve might not be super meaningful for all participants in this exercise. So specifically, if you're trying to learn one model, it is not clear that that one model is going to be useful for everyone in the network. And specifically, because the data that comes from different users is potentially very heterogeneous, it doesn't make sense to find one model W that will work for everybody, despite the fact that we have heterogeneous participants in this network. Okay. So because the goal is to find a model to deploy on each one of the clients, what we would like to do is we would like to personalize that model to the client at hand. Okay, so if you want to find a personalized model to deploy on each one of the clients, then this is the wrong objective to be solving in the first place. You don't necessarily want to find a consensus model that works on average for people, but we would like to learn something that will work for each one of the individual participants. And so what is lacking in this enterprise is personalization. So for instance, going back to the initial example, if we were to predict the next word on a mobile keyword, then we understand that users are very diverse, and what works for Irina might not work for me. Okay, so people have, of course, realized that this is an issue, and we are not the ones to propose this problem. And as things go, whenever problem is discovered, there are a lot of approaches to solving that problem. So there are many different approaches for dealing with personalization in federated learning. Because there are many different approaches, there are different theory that are provided for these approaches. It is very difficult to decide what is best. There are different notions of what best might mean. And what we are trying to do here is we are trying to provide a unifying optimization framework that handles, to the best of our knowledge, most of the approaches for personalization in federated learning. I will discuss different approaches to personalization, but all convex approaches that have been proposed in the literature are covered by the framework that we are going to study next. And so that's kind of like the big picture where we are going. Now, just to briefly tell you what are the kind of classes of personalization approaches. Well, classes are as follows. What people sometimes do is fine-tuning of a model. So, for example, one can solve this wrong objective that is located here on the top left of the slide. We find one global machine learning model, and then we deploy it on different devices, and we can fine-tune a little bit the model. You can think of, say, a one-step update estimator based on the local data. Okay, so this is something that we teach our introductory in our introductory classes. So we can think of, like, if I deploy a model to someone that's kind of reasonably good, I can fine-tune it a little bit by making like one or several steps of updates starting from the global model. That seems to be doing reasonably well, and it's a popular approach in the literature. The approach that I will mostly focus on is focused on multitask learning, which in statistics, for example, could correspond to multiple output, say, regression models. So rather than trying to come up with approaches that predict the scalar, we might think of ways of predicting vectors, and the regression coefficients might be somehow related to each other. And there are other approaches as well. Okay, so what we want to do is we want to provide a unified optimization framework, and therefore we want to study the following optimization problem. So what I'm going to talk to you about is going to be about different ways of optimize this function f, the capital F, which has two parameters. It has a W parameter, which we think of a global or shared parameter and there will be a local parameters that correspond to the task at hand. So, for example, the local parameter beta would specify kind of like maybe the difference compared to the model that's parameterized by W. And if this is not clear at this point, I will give you examples of objectives that are covered by this seemingly looking objective that has nothing to do with what we are discussing so far. Okay, so the big picture is this is the optimization problem that we are going to study. And as it turns out that multitask learning approaches for personalization in federated learning are covered by this objective. They are specific instances of problems of this form. Okay, so in particular, the punchline is that by studying this, we can recover personalized federated learning approaches as a special case. And what we are going to do is, by looking at this unifying framework, is that we are going to provide good optimization guarantees. And what does good mean? Well, we'll think of schemes that have not much communication and also that don't compute too much. We'll specifically be more precise in a bit. Okay, so the goal is minimize this objective and provide minimax optimal optimization theory. So specifically, what does optimal mean? So we would like to have a thing that communicates as little as possible. In particular, we will see that we will match lower bounds on the number of communication. The other thing that we care about is how frequently we compute a gradient with respect to W. So the way people think of optimality in terms of optimization is you can think of that there's an access to an oracle that tells you a gradient, the first order information about your function, and you call that oracle to give you the gradient. And the question is, well, how often do you need to compute, call this oracle? So we'll see that what we can do is we can do as well as any procedure that uses only that kind of information. So any procedure that uses first order information with respect to W and with respect to beta. So that's kind of the setting that we care about. Okay, so now once we provide this optimization theory for minimizing an objective of this form, what can we do this? Well, turns out that we can obtain state-of-the-art guarantee for almost all special cases that have been proposed in the literature. So what does this mean? So the guarantees are in terms of communication and computation. How frequently we need to exchange information with the cloud, with the central server, and how many gradients do we need to compute. And the special cases, we focus on personalized federated learning objectives that exist in the literature. But we also point out that by simply tweaking existing approaches, we can come up with new objectives that potentially will do better. And again, remember, this is a talk about the optimization. And what would be interesting in my mind is to think about what kind of statistical model we can impose on this problem so that some of these optimization procedures are optimal also in the case of statistical properties for these models. There's one instance of a problem that I'm going to describe later that we don't get optimal communication and computation. So we get optimal communication and optimal computation in terms of either W or in terms of beta, but not jointly. So there's a tuning parameter in the algorithm, and by setting that tuning parameter in one way or another, we can either get optimal computation with respect to beta or optimal computation with respect to W, but not both. So potentially there are alternative approaches that can deal with that setting. We'll discuss that in a bit later. Now, what is potentially surprising, or at least it was surprising to me when we established these results, is that we are able to obtain best known results, despite that we don't utilize some special structure. You can imagine that this problem here, this FM, this is the objective that empt machine, empt client has, will have some additional structure. It will have maybe a likelihood plus a penalty type structure. Maybe it's going to have I don't know, something that looks like a smooth function plus something that's convex but proximable. So there could be some additional structure in this function, and we are not using that special structure. The only thing that we're going to assume is that these things are convex and smooth, but nothing beyond that. And you can think that if we impose more structure on this, then a better result could be obtained in either terms of communication or computation. So because of these claims, I'm claiming that we are providing a universal optimization approach for personalized federated learning. Okay, so now let us think about these local objectives. So in order to establish the results, we need to impose ways of how we are going to compute, and also what kind of assumptions we are assuming. So we will consider three different ways to access the local objective. Okay, so we need to, in order to minimize over W and beta, we need to impose some structure on this FM, and we will consider three different structures that people commonly consider in the literature, which is that we might have access to the gradient of these functions. So gradient of this function with respect to W and gradient of this function with respect to beta. Another popular approach, which is used in machine learning, is that of having access to the stochastic gradient. So rather than having access to the exact gradient, which is in case one, we only have estimates here denoted by hat, which are unbiased or have bounded variance of, well, they're unbiased and they have bounded variance. Okay, so the first line tells us that these estimates of the gradients are unbiased. And the second and third line tell us that the gradient with respect to W and gradient with respect to beta have bounded variances. And then finally, an approach that is frequently considered in machine learning is that this structure, the FM functions, they have some special structure. For example, they're written as a finite sum. So it's an average of functions FM. So you can think of this FMI, this is just a loss of your, say, linear model on yi and xi. So this could be yi minus xi w beta. Okay, so a loss at one point, and then to get the whole function, we would average over all the training data points that we have on machine A. So depending on which axis we have to, we'll be able to establish different results. So we will think about access to how many access to these objects we have, or how many access do we need for these gradients to compute. So any questions so far?
Isn't free just a special case of one?
Well, so let's say that you have a million observations. Then computing the gradient in the case one might be computationally hard. So each time you call a gradient, I need to look at all million observations that I have to compute this gradient. In the case here, I'm thinking of the way I'm going to call this computational oracle is I'll ask, well, what is the gradient at observation 100? What is the gradient observed?
Okay, you're not going to use all the eyes. Got it. Thank you. Precisely.
So we are going to think of stochastic gradient descent, and you can think that 2 and 3 are closely related. But the 3 uses the structure that we frequently have in our maximum likelihood estimation type problems, or in problems that involve like fitting a neural network or something else. So that's a great question. Thank you, Irina. Any other comments, questions? Okay, so Of course, we cannot do this without assumptions. So we are going to impose some what we think are reasonable assumptions for the problem. So we will assume that this function f, which is a joint function of w and beta. So this is the global function. This one here, the capital F is the objective that the central server would like to minimize. We're going to assume that that function is jointly strongly convex. Now, there are many problems that are not jointly convex, and it's of interest in the future to develop some unifying theory for non-convex optimization. But at this stage, I think even studying convex problems is quite interesting. The other thing that we need some structure also not only on the global function, but also on individual component functions that sit on different machines. So we need this function to be jointly convex. So we don't require this one to be strongly convex. It's going to be sufficient for this one to be just convex. We will need that this function on each one of the machines is smooth. And the smoothness components are going to be denoted LW and L beta. You can imagine that the rates of convergence for these functions are going to depend for our optimization algorithms are going to depend on these smoothness components. So the smoothness is essentially just a Lipschitz constant for the gradient, or you can think of like an upper bound on the Hessian. So these are the notions that we will use. And also we need, in the case when we are dealing with the finite sum type problems, we are going to denote smoothness with respect to W and beta as this calligraphic L to distinguish it from the smoothness of the whole function. So this last part is only really relevant for dealing with a special type of optimization problems. So now, with these preliminaries, let us take a look at personalized federated learning objectives. So in traditional federated learning, we minimize this thing where, well, this FM is L prime smooth and mu prime strongly convex. And it is known in the literature that optimal communication and computation for this problem is of this form. So you need square root of condition number times log 1 over epsilon to reach an epsilon accurate solution. So you would like to get W hat as a solution to this, and you know that F prime of W hat is close to F W star, where W star is a minimizer, and the difference is epsilon. So you need this much work. Now, you can also think what is the optimal computation when you have a finite sum structure. So if each one of these FMs has a finite sum structure, so it's a sum over n data points on an empty machine, then optimal computation has the following form. It's like n plus square root of n L prime over mu prime log 1 over epsilon. And you can immediately see that for our algorithm that I'm going to describe in section 4 is, well, you can see that this objective is a special case of a personalized federated learning where you set beta m's all to be equal to 0 and you don't optimize them. And it turns out that in our framework, using the optimization algorithm that I'm going to describe later, we can recover both the optimal computation and optimal computation and computation for both finite sum problem and the part where we have access to the gradients. Another example that falls into our framework is the other extreme. So if you think of traditional federated learning, one extreme where you don't have personalization, another kind of potentially naive approach would be, well, why do I even care bothering with fitting, doing any kind of computation? I'm just going to fit the linear model. I'm going to fit some model on each one of the machines separately. So here, these beta 1 through beta m's, they're all d-dimensional vectors, and there's nothing that ties these optimization problems together. So we can simply solve all of these optimization problems separately. And in this case, of course, I don't have to communicate anything. I'm going to fit a optimization problem on each one of the devices separately. No need to communicate, and we know what the optimal first order methods, how much computation do they need to do. So essentially, accelerated gradient descent would work in this case to give us these rates of convergence. Okay, so these are maybe not interesting cases. Now, what has happened in the past 2 years, there has been plethora of papers dealing with some kind of notion of multitask personalization, or some people call it implicit model agnostic meta learning. It's a mouthful, but essentially what it boils down to is solving an optimization problem of the following form. So this paper was written by a co-author of mine, where they're essentially looking at fully kind of personalized problem, but then these beta m's are pulled together. So this beta bar that is located here, this one here, is a average of beta m's. Okay, so what you would like to do is you would like to personalize parameters for each one of the model, but you would like to keep them close to the global average. So you're somehow pulling them together. Like this is kind of like a reasonable way that people study these problems. Another approach that was proposed is closely related. This was kind of at the end of the last year. What was proposed is to solve an optimization of the following form. So each machine is going to identify beta m that is close to some global W. So in order to minimize over W, we internally we solve this beta m, and then we identify W as a global parameter. Okay, so again, we are pulling things together. It turns out that both of these approaches can be written in the following equivalent form. So we can have a objective mx2 that covers both mx and me objectives. So we can rewrite the two problems in the following form, where we have the average of the beta m's plus some shrinkage towards global parameter W. Okay, so I think this is very intuitive. Like you have some parameter towards which you are trying to shrink all of the beta m's. So you can think of fitting number of linear models, and there's some parameter W to which you are pulling all of your individual beta m's. Okay, so in particular, what is important, and I'll show you later in simulations, is to scale appropriately the global parameter W by square root of the number of participants in this operation to get the optimal convergence rates. Otherwise, the gradient descent behaves erratically, as we'll see in the simulations. Okay, so this function. So now we have this objective. What we need to verify is what are the kind of parameters of this problem. And it turns out that if we assume that these individual functions are L smooth and strongly convex, then the optimal communication is square root of smaller between L prime and lambda divided by mu prime times log 1 over epsilon. Optimal number of gradient steps is square root of condition number log 1 over epsilon. And similarly, we can recover these optimal rates when lambda and L prime are of similar order. Okay, so this is one set of multitask problems that people care about, and using the optimization algorithm that I'm going to tell you in a little bit about, we get these rates. Another approach, which is closely related to the morale envelope approach we saw earlier, is the one that's shrinking towards the global solution. So this W star is the solution to the traditional federated learning. So rather than optimizing this together with betas, you first solve the problem for the global W, and then you shrink each individual parameters towards this parameter W. That again can be cast as an optimization problem on the previous slide, and well, we can cast it. We cast it in this form, where we have a well. So in order to recover this objective, what we need is that the capital lambda tends to infinity. So if capital lambda tends to infinity, then the W is going to be the solution of a traditional federated learning, and the beta M would be solution to this objective. But an interesting case is that hasn't been studied in the literature is what happens when lambda does not, capital lambda does not tend to infinity. In that case, we get some interesting behavior. And so we get, again, that this is recovered. We get these communication number of gradients and stochastic gradients for sufficiently large capital lambda. So as soon as capital lambda is bigger than 3/2 times the lambda over mu, then we get the optimal communication and computation for either one of the Oracle models for computation. And there are, as I promised, many other approaches in the literature. People have been writing many papers in this area, and it turns out that for these convex approaches, we can recover the theoretical guarantees in our framework. And what is potentially something that it would be interesting to do in the future is what happens with things like with approaches that use meta learning, where you learn a global model and you fine tune it on each one of the machines. These are inherently non-convex, and that's something that could be of interest in the future to study. Okay, so now so just to kind of remind you what the big picture is. So the big picture is to study all of these personalized federated learning approaches through the lens of unified optimization objective. So when we have unified optimization objective, we need to think what are the convexity parameter and what are the smoothness parameters for each one of these specific problems. So each one of the instance of these problems gives you smoothness and convexity parameters for the original problem. And then our theory tells us what the communication and computation is. And it turns out that these, in many cases, match the lower bounds. So what are the algorithms? We investigate 3 algorithms depending on what kind of access to the oracle we have. So we either have access to the gradient, we have access to the stochastic gradient, or we have access to the finite sum oracle. But morally, all of these work in a similar way. So the local HGD approach, what it does is it proceeds in rounds. So there are, in each iteration, we either compute the gradient step for W and beta, and every tau rounds, we submit the W's to the central server, which updates the W's and sends this W back to the users. So you either perform these averages, you either run stochastic gradient with respect to beta, and you run local HGD with respect to W, and every T round you average the W's that you have on each one of the machine, and you send it back to the devices. So this averaging requires communication, and these operations only require local computation. This is one algorithm. So the question is then, how many iterations do you need to reach epsilon solution? Well, this kind of depends on how accurate your stochastic gradients are, and how diverse the distributions are between the machines. So this zeta star here tells you something about the divergence of the gradients at optimum. So W star and beta star are optimal parameters, and then this tells you something about how the gradients are different at optima at different machines. These red terms correspond to the iteration complexity of stochastic gradient descent to minimize the local function when W is fixed. And these things in orange correspond to iteration complexity of local SGD to minimize function f for fixed beta. Is there a question? Simon?
Oh, sorry, I accidentally touched the mute button. Sorry.
Oh, okay. I guess anybody else do you folks have questions? Okay, so if no questions, then okay. So if you're familiar with the rates and literature, then these both terms would not necessarily surprise you. What we advocate as a thing that will do really well is to run a randomized coordinate descent. So in particular, the randomized coordinate descent proceeds as follows. You flip a biased coin with probability PW. You update W in order to, and with probability P beta, so PW plus P beta will sum up to 1. With probability P beta, you just perform local computation. So with probability PW, in order to update W's, you need to run kind of global communication step, and otherwise you just do local communication. So the thing that does really well is accelerated coordinate descent for this personalized federated learning. So the coordinate descent here is like it's a randomized coordinate descent. So with some probability you choose W, with some probability you choose beta. The probability of choosing W is a parameter that is going to tell you on average how often you need to communicate. And the optimal, what theory suggests is to use the following choice of the parameters. So with these choice of parameters, one gets the desired rate of convergence. So in order to reach epsilon accuracy, one needs this many communications, this many computations with respect to W, and this many computations with respect to with the local parameter beta. So all three are optimal. So we can construct an instance of the optimization problem for which no first order method can define epsilon accurate solution with fewer either gradient computations or fewer communication rounds. And the other thing that we investigate is accelerated stochastic coordinate descent with variance reduction when we have when we have this local sum. So in this case, maybe to Irina's point earlier, because FM is the average of the local observations, when we compute the gradient, we only take one observation I to make an update, and this I is chosen at random. And then with probability beta, we update the local parameter beta again by one stochastic gradient descent update. And it turns out that in this case, if you combine this stochastic coordinate descent idea with variance reduction plus acceleration, then we recover the following. We recover the optimal communication for this type of problem, and we recover the optimal computation, but not simultaneously. So there's a tuning parameter in the algorithm that we need to choose, which either gives us optimal computation with respect to the gradients of W, or with respect to the computation of gradients with respect to beta. Okay, so now just quickly, I'll show you a few experiments and I'll come to conclusion. I realize I only have 2 minutes maybe left. So the first point is that the algorithms converge. So they require some number of communication rounds to reach accurate solutions. So here we have different objectives. So here I don't really run the procedure to see which one is going to be personalizing better. Simply, we are using objectives that people have used in the past for personalization, and we are comparing 3 different optimization algorithms for these problems. And what we can see is that stochastic coordinate descent and stochastic variance reduced coordinate descent do much better compared to local SGD, which is de facto standard for these problems. Another thing that we illustrate in the experiments is that we need reparametrization of the global parameter W by square root of number of machines, number of devices, because otherwise the iteration is quite unstable. So the red curve corresponds to the gradient descent. Well, it corresponds to our procedure when we don't use the correct parametrization. The other thing that is useful to observe is that the probability of communication. So when we are running accelerated coordinate descent, we need to communicate every so often. That is controlled by how frequently update W. And by setting the probability of updating W according to the theory, we get the best sort of communication and computation rates. Okay, and so this gets us to the end. There are numerous, I think, questions and very little answers. So one thing that is missing from our work is that typically in federated learning, people consider partial participation. So in the development of our framework, we were assuming that every one of the edge devices will provide us with updates at the communication round. What really happens in implementation of in real world implementation of these approaches is that you're subsampling the devices that are going to give you updates. So out of, like, say, million observations, maybe you're going to perform an update based on 100 edge devices. The other thing that maybe I did not emphasize enough in the talk is that we are providing minimax optimal rates under the assumptions that we have. So we impose fairly general assumptions on the functions f, such as smoothness and convexity. And these assumptions don't necessarily exploit all of the structure that one may have in the optimization problem. So potentially you could have a better rate if you assume more, which is not surprising, but potentially if you do have more structure in your optimization problem, you should use that. And potentially a different optimization algorithm should be developed to utilize problem-specific structures. Development of improved personalization, as well as development of statistical theory for what approaches generalize well under different assumptions is quite missing in the literature in general. And I think people who work on meta-learning, people who work on random effects models would probably have quite a lot to say about development of theory here. So, I invite you to think about these problems, because you probably have the right tools to solve important problems in this area. And this is kind of my hope to work on next. So if anybody has interesting ideas, I would be very happy to talk more and potentially collaborate. And then finally, the thing that we have not touched at all in our work is what can be said about optimization for non-convex objectives, which is actually what people use quite often in practice. So they either use deep learning in the federated setting, or they are using model agnostic meta learning approaches, which are inherently non-convex, and saying something about communication and number of iterations to reach absolute accuracy of a stationary point would be quite interesting as well. So this is all I have, folks. I went over my, well, I'm around 55 minutes. The more information is found here. And thank you so much for listening.
Okay, thank you very much, Dr. Kolar, for a very nice talk. And I guess we may have time for a couple of questions. So,
hi, I have a question. Thank you for this great talk. I was thinking about a varying coefficient regression model, where the regression coefficient may depend on each individual. So I was wondering whether that model can be considered or solved maybe as a special case of this personalized federated learning. I'm not sure whether my question is clear.
So let me just maybe rephrase. So you have like maybe say partially linear model or something like that. So you have like a model would be Y is X beta plus Z beta J plus noise, where beta J is a user specific and maybe depends on varying coefficients.
The second, the later one, the beta J depends on each individual. So maybe it is also a function of other variables like.
I see. So Y would be X beta J of Z, something like that.
Yes.
So this is okay. So I guess like the difference here is that you would have to think about how to make the problem non-parametric. So for instance, if I let's say use B-spline basis expansion of your varying coefficients, then everything becomes sort of a parametric model which perfectly fits into this framework. Now, if you want to keep around these infinite dimensional objects like beta of Zj or beta J of Z, I'm not quite sure how would I algorithmically deal with that, but I think it's definitely something that falls within this framework, and it would be interesting to study in either from optimization perspective or from statistical perspective.
Okay, thank you.
okay, maybe one more quick question for Dr. Kolar, if somebody wants to ask something.
Hi, yeah, this is Hui Yan. I really enjoy your talk, and I'm just kind of curious. I think in your formulation about the personalized federated learning and also some of the cited work, it seems like the penalty term is mainly there's like a global, like there's a global mean for the beta, and then it's kind of similar as some kind of random effects model for it. I'm just curious that like in this context, is that actually reasonable to assume there's more heterogeneity in your data such that there might be a few, so it's not local, but you see it's probably your personal devices can be grouped into several, smaller categories, and each category is probably can be modeled with like a kind of a local random effects.
I think that makes a lot of sense. Off top of my head, I am not aware if somebody has done that, but from the application perspective, I think it makes quite a lot of sense. I mean, you could think of regionally localizing algorithms on each one of the devices. So for example, let's say that you are interested in advertising, and you would like to advertise differently for different regions, maybe in Chicago area, in kind of Houston, Austin kind of area, and in Texas, you would have a different model. And so for users inside of Chicago area, you would have like one parameter maybe that governs kind of the pooling, and in Texas, maybe you would have a different type of parameter. So I think from application perspectives, there are numerous applications where this makes sense. Potentially somebody has explored this in the literature, but I must say that my take on this is that there has been a lot of reinventing the wheel happening in the literature, and I don't think this necessarily in a good way. So I think that there's a lot of there could be a lot of benefit of educating people in the machine learning community about what people have done in the random effects model, 30 years ago in statistics. So I think there's a very kind of good potential for writing, bringing useful tools to this area, because there are a lot of interesting problems.
Yeah, thank you. And also, have you seen maybe like Bayesian personalized federated learning work in the literature?
So there has been some work on variational inference that I'm aware of. More generally, I have not seen much, but people must have been thinking. So there's a group at CMU. I forgot exactly who the lead author was. I saw the students talk, but there's a group, I think maybe Amit Talwalkar has done some recent work where they thought of variational inference for Bayesian models in this setting.
I see. Okay. Yes. Thank you very much for information. Yeah.
Sure. I mean, so I think like variational inference is something that is maybe popular in machine learning, but it loses quite a lot of information about uncertainty. So there's for sure a lot of opportunities to think of maybe more different Bayesian approaches that also give you valid uncertainty for the things that you are computing. Because if I talk to my colleagues in marketing group here at University of Chicago, they really dislike the variational based approaches because it underestimates quite a lot the uncertainty of the in the posterior. So I think development of other techniques is would be valuable.
Thank you.
Okay, so let's thank our speaker again for this very nice and exciting talk. And I think that's it for this week's seminar.
Okay, thank you very much,
Dr. Kolar. Bye.
Having me. Have a nice weekend, folks.
Thank you. I think everyone is leaving now.
Okay, so